What we're going to look at here is a recreation of experiment to discuss the kinetic theory of matter. The kinetic theory of matter, remember, is that all molecules and atoms are in constant motion. That motion comes because of energy. That energy results in that motion, that the warmer something is, the more energy that it has, the more that it moves, the more motion that it has. So what we have here are three different measuring devices with water in it. Doesn't matter that the volumes are a little bit different. And from the left we have ice water. In the middle we have temperature or water from the tap. And on the right we have boiling water. It had been poured out of a boiling beaker and it's been a little bit cooled, but it is quite warm. What I'm going to do is add a drop or two of food coloring. Let's start with just one drop of food coloring to each one of the devices. And notice the differences in how the colors mix. Now we would anticipate that the left two, that which is freezing and that which is room temperature, would be very similar because the temperature difference between the two is only probably somewhere in the neighborhood of 40 degrees Fahrenheit. But between the left two and the right one, notice that the right device has water that's a little bit cooler than 212 degrees Fahrenheit. So the difference there is more like 140 degrees. And so because of the rapid motion of the molecules, because of the higher temperature, the mixing is taking place much faster. Now there's no physical mixing taking place from any device. I didn't mix them. The water was still, up to my eye apparently, it was just sitting there still, and I added the food coloring. What's mixing the food coloring are the molecules of water themselves moving inside of the devices. So though it looks like it's water sitting at rest, when it's at rest, remember that the molecules are constantly in motion. Notice how on the left, the coloring has mostly dropped to the bottom, and it will mix over time. The center, it's mixing more rapidly than the cooler, but not nearly as fast as the one on the right. So again, what this is showing is that the molecules of water themselves are in motion, even when they appear to be at rest. That they are in motion, that there is a higher level of motion with a higher temperature. That higher temperature translates from the higher level of energy in those molecules. We're just going to go ahead and let this video run for a while. And notice that the one on the right is fully mixed. The one in the center seems to have a top and bottom with different lines of coloring as it falls. And on the left, the coloring is mostly fallen to the bottom. And again, over time you would see that this color on the left even will completely mix and look like the device on the right. However, it's going to take a much longer period of time for that to occur. All right, quick review. Yesterday we talked about the two major change categories that we have, physical changes and chemical changes. Yes, ma'am. Okay. So physical changes and chemical changes. Physical changes are primarily in the way things look. We don't really actually change the atoms or molecules that make it up. We just put them in, make them look different. I use the example of cutting up the piece of paper. That same example is in the book. So it's kind of like my mother taught my son that when he was expected to eat all of the food on his plate, that one trick he could do is just to spread it around the plate, right? Rather than leaving all the peas in one little clump, if he spread them all around the plate, it looked like, of course, I told my mother that's teaching him deceit. But anyway, to her it was kind of funny, you know, so spread them around a little bit. So, and actually she was saying it for herself because she grew up, you know, just post-depression, eat everything on your plate. Oh, by the way, if you want to make grandma feel better, just spread it around a little bit and you won't have to eat everything. So it was kind of like deceive me, which maybe made it a little bit better, a little bit more okay. But so the physical change there, when he spread the food around, he didn't change anything. He just made it look different. And we can take matter and material, make it look different, or we can react it And which one of these two did we say is the easiest to undo? Physical, right. Because we can think about it as we can put something back together. But if we change it, we have to unchange it. If we morph it into something else, it's harder to unmorph. Now, reactions can be reversible, but it's not necessarily easy to do. It's actually easier to tape together and reconnect the fibers to a ripped piece of paper than it is to unburn a piece of paper. Okay? So that's the idea. Talked about phase changes in the second section. Solids to liquids, and also liquids to gases, and we talked about solids to gases. And this one here, just reminding about the melting point or the freezing point. It's that point where the appearance goes from that of a solid to that of a liquid. If we think of water, when it melts, when an ice cube melts into liquid water, the melting point going the other way, when we have liquid water and it suddenly becomes ice, it's become solid, that's the freezing point, but it's the same point. All right, and so that's a physical change. We haven't changed the water molecules in any way. All we've done is change the way they appear as solid or as liquid. And same thing as liquid or gas, the boiling point and the condensing point. Okay, and that happens at a temperature, 212, the boiling point. Also, that is the condensing point. Okay, but we tend to think in terms of liquid. The freezing point is liquid becomes solid. The boiling point is when liquid becomes a gas. So we tend to think in terms of relative to the liquid. But that is the same point. And again, moving to the right, going from a solid to a liquid, from a liquid to a gas, the red arrow indicates that we're adding energy to the system. So greater energy, think of it as heat. As we heat something up, okay, it transitions from ice to liquid to gas, it boils. As we cool something down, that's going to be taking energy out of it, not putting energy into it, but taking energy out of it. We go from a gas to a liquid, and it condenses. From a liquid to a solid, we call that freezing. We're taking energy out of it. We're having the temperature drop. In the case of sublimating, going from from a solid to a gas, skipping the liquid phase. I mentioned that as well. So, we said the main difference between the different phases of matter is the volume that they occupy. When I took that jug and I capped it, and it started to cool, okay, it had a certain volume of air in it. A little bit of water, but mostly air in it. And as it cooled, that same amount of matter, you agree when I capped it, nothing could get in and nothing could get out. I trapped everything inside and kept everything else out. So we've got a certain amount of matter in that jug. As it cooled, it takes up less volume, and the matter inside starts to shrink. The container that it's in also begins to shrink because the vacuum created inside is stronger than the walls of the container. Okay, so that's why the jug started to deform. And it's going to sit in the freezer for another 15 minutes. It's going to deform even more, so we can look at it before we go. How much more is it going to deform as it cools in the freezer? But the same matter, it's the same water-air mixture in the jug. No more is getting in, none's getting out. But yet the amount of space it takes up is changing. And the container is changing to fit. I mean, have you ever had, for example, balloons? And you leave the balloons in the car overnight and it's cold. You go back out and the balloons are all shriveled up. And as they warm up, they kind of reinflate. Or maybe you've had plastic soda bottles and you've had them in the car. They were empty, but you capped them again. You come out to the car in the morning after it's been cold and they're all puckered in and closed. And if you open one of them up, what's going to happen? It fills the space again, right? Because atmospheric pressure comes in, boom, it fills the space. What happens if you take it then, all these other bottles are puckered up, but you open one up and it reinflates and you cap it and put it down. Now what's going to happen? As the day warms up, those other bottles are going to warm up and they're going to go back to normal shape. The one that was normal shape is now going to have pressure inside of it and it may even bulge a little bit. Okay, because what's in it is now taking up more space. Those that were puckered and go back to normal shape have returned to about the same volume that they used to have. But you messed it up because you opened up one of them and you let cold air in. And now that cold air is warming up and it's trying to expand and it's pressing out against the bottle. And you can feel it, rather than just being a normal bottle, when you grab that, you can feel it's a little bit oversized, a little bit plump, right? And you squeeze it and it resists your squeeze more than the other bottles. Why? Because it's already pressing out against the walls. The other ones are just kind of here, okay? This one's trying to get bigger and it can't, so it's feeling you feel the pressure of that on the inside. So this all goes back to, we talk about stuff moving, the kinetic theory of matter. This is where we're picking up on new stuff today. The kinetic theory of matter says that all molecules or atoms are in constant motion. So think back to the 3 measured containers in front of you here that have the purple food coloring in it. Why was the warmest one, why did it change color the quickest? Well, it's related to the same factors that made all of them change. Remember I said I didn't stir anything. I just dropped the food coloring in. What did the food coloring do? The food coloring mixed into the liquid. It mixed in at different rates, and hopefully you picked up the fact that the warmer the liquid is, the faster it mixed. But it didn't require me to mix it. The molecules of water that were in the containers are constantly in motion. The water mixed itself. The water mixed the food coloring into the water. I didn't have to do it. Even at 32 degrees, there was motion of the molecules of water that mixed the food coloring into it. Well, we've talked about this before as a theory, but at what temperature is there no motion? Do you remember? We get to a certain place where the motion stops. That's absolute zero. At absolute zero, there is no motion, which means there's no time, because time only has meaning when there's motion. With no motion, there's no meaning. Absolute zero, theoretically, the electrons stop spinning, both around the nucleus and around their own axis. Okay, so there's no, but everything above absolute zero, which we've never been to, it's theoretical, there's motion. There's energy. And each one of those samples has energy in it. That energy is creating motion. The molecules of water are moving all the time. Ice water, the molecules are moving. Boiling water, the molecules are moving. And not because of the water, not because of the bubbling action from the heat. The molecules and atoms are in motion all the time. And in this experiment, the molecules of water mix the food coloring into the water. Now, the fact that the warmest one mixed the quickest tells you what? The molecules that are the warmest are doing what differently than the ones that are cold? Ma'am? Moving faster. So as opposed to kind of like, yeah, I'll get there eventually, they're like zipping all over the place, boom. And every time they bump into a molecule of food coloring, they carry some of it along with them. So very quickly, the hot fluid has the color completely mixed. The cooler the fluid, the less motion, the longer it takes to mix itself. But given enough time, will it mix the food coloring completely through so that all 3 look exactly the same? If I put the same amount of food coloring in the same amount of water at different temperatures, eventually they will all look the same, as long as we're above absolute zero and stuff is moving. It might take a really long period of time, kind of like watching glass flow. You know, windows, it takes a long time. Most people think that glass is a solid. It's not. It's liquid. Okay? How do you know that glass is a liquid? When I lived in New York the second time, from about 1998 until 2012, okay, my parents lived in an 1880s brick Victorian that they ran as a bed and breakfast. And in that brick Victorian, you looked at the windows, the tops of the window panes were really thin, and the bottoms of the window panes were really thick. Why? Because the glass was flowing top to bottom. Gravity was pulling the glass down. Now, it took more than 100 years for that to happen, but again, it was moving. It will happen eventually. Eventually, those windows would completely flow to the bottom and be a pool of glass with nothing that looked like a solid piece of glass, because you see glass as a solid, but it's a slow-moving liquid. Okay? So it's the time scale that makes it look like one thing or another. Will the glass eventually flow all the way down? Yes, it will. Will the color eventually be completely mixed? Yes, it will, but we don't know how long it's going to take. It may take an incredibly, in our minds, a long time to do. Let me get back on notes. Okay, so motion is required for this to happen, and motion requires work. And work requires energy. So the question is, where does the material get the energy to do the work to move? Where does it come from? And the answer is from the surroundings. How did the water boil? It took the energy from the hot plate. Okay? So as the environment, these glasses right now, hopefully this makes sense to you. Think of it this way. The center glass is at room temperature, right? Is its temperature changing? No, it's at equilibrium with the room temperature, right? It's not changing. This container here that has ice water in it, is its temperature changing? What is it doing? It's warming. Why? Well, the surrounding environment has more energy in it than it does, and so it is drawing energy from the surrounding into itself. When will it stop getting warmer? When it's at room temperature, right? When it's got the same temperature as the surroundings. What's happening over here? This boiling water. It's cooling, right? So around it is a certain energy level. We sense that as a temperature. In here's another temperature. This is a higher temperature, more energy. So it's dissipating energy, and the room is drawing energy from it. This and the water over there in the hot plate is actually raising the energy level of the air in the room. This one is sucking in energy from the room because it's cold, and this one's just sitting here saying, stop messing with me, I'm fine where I'm at. Okay, so there's three different energy situations here. The hot one is giving off energy and heating the room. The cold one is drawing energy in and cooling the room. Now the energy that's here, let's say that there's certain energy in this room, and all we had was the hot one. We had a big swimming pool full of hot water. You get, of course, that the temperature in the room would rise. It would start being warm in here because the energy is going out, and it would continue to rise until the temperature was the same throughout everything. Okay? This cold one, it's drawing energy in. As the cold one draws energy in, it decreases the energy you have. It would cool the room. You see that? So think of it this way. The hot thing is giving energy off to you and warming you up. The cold one is drawing energy in and is cooling you. So cold things cool, hot things warm. Makes sense. That makes intuitive sense to us. That's the way we live our lives. Hey, let me go get a soda and put it in the fireplace because I need a cool drink. You're like, what? You put it in someplace hot to warm it up. Oh, but when the cold thing is being warmed up, the hot thing is being cooled. Like a radiator, right? And a heat exchanger in your car. The radiator is drawing energy out of the coolant, right? So it's heating up the coolant, but it's then cooling down the engine. Or you can think of it this way, the engine's heating up, and it's then heating up the coolant. So when energy goes from one place to another, it changes temperatures. You take the coolant, you go through the engine, the coolant raises the energy, the engine raises the energy of the coolant, therefore cooling itself, and then that hot energy in the fluid form goes back through the heat exchanger to for the heat, right? That's a second radiator, a small radiator. And what it does is it takes energy in the fluid, puts it back into the air and blows it into the compartment so you can get warmed up or defrost your windows. Okay? That heating of the air in the compartment cools the coolant. It's a second radiator. So that's why when you have a 1986 Olds Calais, you're driving it around and you're starting to overheat in the middle of the summer, the first thing you do is you turn on the heater. It feels nasty because you're living in Southern California. I'm not like I'm speaking from experience, okay, but I am. It's hot in California, middle of the summer, and your temperature gauge is going above red line, and you turn on the heater full blast. Why? Now you have two radiators working for you. Yeah, you're going to suffer because the engine heat's going to come onto your body, but you know what? Hopefully you can keep the engine cool enough to make it home. So the matter draws energy from its surroundings. Or you can say the other way too, the surroundings may draw energy from the matter. Okay, because if the room is cooler, like in the freezer right now, it's drawing energy from the air and water that's in the jug. But energy is being transferred between the surroundings and the matter. Okay, so the higher the temperature, the greater the molecules or the atoms' speed. Is what this experiment demonstrated. The speed of the molecules for the hot sample was much greater than the room temperature and for the cold one, which is why it mixed pretty quick. I mean, you almost had to be looking for it because it happened so quickly. And in contrast, by the other two sitting beside it, you could say, hey, it's happening. But see, even look now. As you look at it, it's still not completely even. There's still swirls where the food coloring fell. It's not fully dissolved or fully mixed in yet. Higher temperatures, greater motion. Hopefully that makes sense to you. Again, all molecules and atoms, they're in constant motion. Here's the deal, though. They are in motion in different ways. You're going to get sick of me doing this, but this is something I want you to kind of like memorize. And if you're sitting in an exam and you do this, that's cool. That's fine. Okay? Remember, like we said, you know, Roy G. Biv and all that kind of stuff? Like right now, we've got solids. Solids are always in motion. This podium right now is in motion. Now, do you believe me? Because you look at it and say, but Mr. Baker, the podium's not moving anywhere. It's not going anyplace. Well, here's the deal. Its motion is vibration. Solids vibrate. Matter of fact, I do this generally. Put my hands together. This is a solid. Solids are vibrating. This solid podium is vibrating right now. The molecules and atoms inside each other are vibrating against each other like this all the time. But it's not moving. Why? Because for every motion that's going in one direction, there's an equal and opposite motion going in another direction. And the net result is no motion. Okay? The net result is no motion. That does not mean there's no motion. The net result is no motion. Think of it this way. We did positive and negative charges. We said if they're positive and negatives and they're perfectly balanced, the net charge is 0. Okay? Just in the same way the net charge is 0, the net motion is 0. For every motion that's coming forward just a touch, there's a motion going backwards just a touch, and the net effect is it doesn't move. So solids are in motion and they vibrate. Liquids move in proximity. So what I generally do is take my hands, put them together. This is solid. This, wringing my hands, is liquid. I wring my hands for liquid. Why? The molecules and atoms, they are in motion. They're in motion in proximity to one another. They're touching and banging into each other all the time, but they're moving like this. Okay? They're staying kind of close. They're attracted to one another. So they're staying close, but they're not, they've got more energy. They've got too much energy to stay still and vibrate. They break free because they have more energy, but they don't break free enough to run away from home. They break free enough to kind of like, I'm running away, I'm going to go in the backyard and hide. Okay, like when you're a kid, you know, you eventually come back in. You don't go that far away. That's a liquid. So solids vibrate. Liquids move in proximity. They're basically bumping into each other all the time. But they're moving. That's what's happening here with these three different, whether it's the ice water is moving. Now quick, look, watch my hands. There's the ice water moving. Okay, and then there's room temperature moving. And then there's the boiling water moving. Okay, which is hard to do with a broken wrist, by the way. But anyway, so it's motion all the time. Why did that food coloring mix thoroughly, quickly in the hot water? Because every time these molecules are moving around so fast, they kept bumping into food coloring and pulling along with them. The ice water is kind of like, yo, when I get there, eventually I'll bump into a molecule of food coloring and take it with me. What happens next, though? Well, gases, they're moving in proximity, but they move at a distance. A greater distance from one another. So for my hand motions for the different phases, there's solids vibrate, liquids move in proximity, and then you get to be like a cheerleader. Yay, gases are all over the place, bouncing all over the place, right? They're actually bumping into each other less than liquids because liquids are always pretty much touching each other, bumping around, moving around, playing bumper cars. But then when they turn into gases, they're pushing each other apart. They're moving a lot. They're outside here, pushing away, pushing away, pushing away. So gases, liquids, solids. Think of it as ice melts the water and then turns to steam. Steam condenses into solid, or excuse me, condenses into liquid and then freezes in the freezer. So the ice cubes are shivering. They're vibrating back and forth. Okay? Here is the basic progression. I have a certain amount of temperature in the room. If I increase the temperature in the room, the environment, it'll increase the temperature of my matter. As the temperature increases in my matter, it has an increasing energy level. That increasing energy level creates an increase in motion. The increase in motion creates an increase in distance between the molecules, and that increase in distance is a phase change. But nothing has happened to the molecules or atoms to fundamentally change what they are. It's H2O the whole way through. It's H2O when it's ice. It's H2O when it's liquid. It's H2O when it's steam. All that's different, well, I say all that's different, the primary thing that's different is the volume, which means the space between the molecules. Gas has a lot of space between the molecules. Water has some space between the molecules. Solids have very little space between the molecules. That's the only difference. The reason we can't see water vapor is because the H2O molecules have lots of other stuff between them. Okay? The reason we can't see water in the air is the same reason we can't see sugar in water. Because sugar has water around it and disappears. Here, water in the air has oxygen, nitrogen, carbon dioxide around it. And so we can't see it anymore. But if we were able to collect them all together, we would suddenly have liquid. And if we collect those together even tighter, and we get them tighter by taking energy out, which is shown here, we decrease the temperature, decreases the energy, decreases the motion, decreases the distance, and have a phase change. The decreasing energy takes us from a gas to a liquid to a solid. Increasing energy takes us from a solid to a liquid to a gas over time. So, if a substance is heated 10 degrees, okay, you've got something, and then you increase the temperature by 10 degrees, will its molecules be moving faster or slower? Faster. You've added energy, you've added motion, it's going faster. Will the molecules be closer together or farther apart? They're farther apart. They're farther apart because the increasing energy creates the increasing motion, creates the increasing distance. All right? We're going to start density tomorrow, but let me go get our air jug real quick. And let me ask you to please, nobody stand up.
Good feeling about it after you get done. Excuse me.
And for some reason, I had a high degree of confidence that nobody would be standing up. There we go. See the deformations?
Exactly the opposite.
Exactly the opposite of what he thought, right. So, the same amount of matter that was in there before now takes up less volume. Why? The freezer took energy out of the material in here. It took energy out of the water, a little bit of water in there, and energy out of the warm air that was in here. When it took the energy out of that warmth, took the energy out of the warm matter, it decreased the velocity of the atoms or molecules, which caused them to come closer together, which created a vacuum which the side walls here had to fight against. And apparently they didn't do such a great job because they started to collapse in on themselves. If I were to take this now and heat it back up to, let's say, the temperature that it was before, what would happen to the side walls? They would expand, and it would be back to its normal shape. And if I heat it beyond that point, what would happen? Correct. It would continue to expand, eventually blow the lid off. Boom. And then it would immediately equalize to the room around it. Okay? So that's the kinetic theory of matter. The kinetic theory of matter is about molecules and atoms are always in motion. What is their motion? And that's what the word kinetic means, motion, movement. Okay, as opposed to static, it's kinetic. Okay? Instead of potential, it's kinetic. So it's moving. It's energy of motion. That the energy in the environment affects the matter by, if it adds energy to the matter, it increases the velocity of the matter. And at certain points of increased velocity, which we see also as temperature, directly related to temperature, as temperature goes up, velocity goes up. At certain points, the matter appears to change its form in the form of phase. from a liquid to a gas or from a liquid to a solid. As the distance between the molecules increases, it goes from a solid to a liquid to a gas. As the distance between the molecules decreases, it goes from a gas to a liquid to a solid. You make it closer together by decreasing the energy, which decreases the motion, which causes them to stick closer together. The kinetic theory of matter.